In this example from section 12.5, find the curvature and the radius of curvature for the equation y equals 2x plus 4 over x for x equals 1. You can pause the video now, try this one on your own, and then come back to check your solution. Now, since the path is already given in terms of y in terms of x, the formula that we'll use would be the first one here, which uses y double prime and y prime. So if y is equal to 2x plus 4 over x, if you write it like 2x plus 4x to the negative 1 power, then your y prime, the derivative is 2 minus 4x to the negative 2 power. And your second derivative, y double prime, is 8x to the negative 3 power. Now these can be simplified to 2 minus 4 over x squared and 8 over x to the third power. Now we can plug in for x equals 1, we can determine the value for y prime and y double prime. At x equals 1, y prime is equal to 2 minus 4 over 1 squared, 2 minus 4, which is equal to negative 2. And y double prime would equal 8 over 1 to the third, so that would equal 8. So by doing those substitutions, we can plug the values into the k formula. So k would equal the absolute value of y double prime in the numerator, 8 over, and in brackets, 1 plus y prime is negative 2 squared, and then all of that to the 3/2 power. This can be simplified to 8 over 5 to the 3/2 power. That's going to be our curvature. The radius of the curvature is the reciprocal, 5 to the 3/2 divided by 8. Going back to the PowerPoint presentation, we're looking at applications of this notion of arc length and curvature. There are many applications in physics and engineering dynamics that involve the relationships among speed, arc length, curvature, and acceleration. One such application concerns frictional force. A moving object with mass m is in contact with a stationary object. The total force required to produce an acceleration a along a given path is F, that's your vector for force, is equal to mass times the acceleration vector. Now you can also write this in terms of the tangent and a normal vector using the tangential and normal components of acceleration. The portion of this total force that is supplied by the stationary object is called the force of friction. For example, if a car moving with constant speed is rounding a turn, the roadway exerts a frictional force that keeps the car from sliding off the road. If the car is not sliding, the frictional force is perpendicular to the direction of motion and has magnitude equal to the normal component of acceleration. The potential frictional force of a road around a turn can be increased by banking the roadway. In this example, we're looking at a 360 kilogram go-kart is driven at a speed of 60 kilometers per hour around a circular racetrack of radius 12 meters. To keep the cart from skidding off course, what frictional force must the track surface exert on the tires? The frictional force must equal the mass times the normal component of acceleration. For the circular path, you know that the curvature is equal to the reciprocal of the radius. In this case, the radius was 12, so the curvature can be measured as 1 over 12. Therefore, the frictional force, or the normal component of acceleration, mass times the acceleration, that normal component, is equal to mass times that curvature times the derivative of s with respect to t squared, where s is that arc length parameter. That can be calculated with a mass of 360 grams, that curvature of 1 over 12, and the derivative of s with respect to t of 60,000 miles, 60,000 minutes per 3,600 seconds squared. This is approximately 8,333 kilograms per meter per second squared.